Ukraine, September 2022. A Ukrainian power substation in the Odessa region ceases to function at approximately 2 in the morning when an object traveling at roughly 180 kilometers per hour impacts its transformer array. The object weighs approximately 200 kilograms. It has a wingspan of approximately 2.5 meters. It has no pilot. It was not detected by the radar systems covering the sector until it was within a distance at which interception required a surface-to-air missile costing between $100,000 and $500,000 to destroy a platform that had cost its operators approximately $20,000 to produce. The exchange had been calculated in advance. It was not a coincidence. It was the operating logic of a weapon system that had been designed from its first drawing not to win an engagement in the air, but to win an argument about cost that its opponents could not sustain indefinitely. The problem that Iran's defense industrial establishment had been working to resolve since the early 2000s was not new, but the parameters defining it had shifted in ways that conventional military procurement could not address. The Islamic Republic of Iran operated under a sanctions regime that restricted its access to advanced aerospace technology, precision manufacturing equipment, and the electronic components required to build competitive, conventional military aircraft. The air force that Iran could field against regional adversaries or American power projection assets in the Gulf was, by the second decade of the 21st century, composed primarily of systems either aging to the point of marginal operational relevance or domestically produced to specifications that could not match the capabilities of Israeli F-35s or American carrier aviation. The asymmetric response to this deficit had been developing across several concurrent programs: ballistic missiles, naval mines, proxy force equipment. But none of these addressed the specific problem of reaching fixed targets at medium range with sufficient volume and frequency to overwhelm defensive systems without exposing Iranian territory, or personnel to direct retaliation. The cruise missile programs that Iran had been developing since the 1990s were capable, but expensive to produce in the quantities that a saturation attack strategy required. What was needed was a platform cheap enough to expend freely, simple enough to manufacture at scale, without restricted components, accurate enough to strike infrastructure targets with consistent effect, and numerous enough to present air defense networks with a volume problem that no finite missile inventory could resolve economically. The Shahed 136 was the answer that the Shahed Aviation Industries Research Center produced to this specific brief, and its answer was not a technological breakthrough. It was an engineering economy. The Shahed 136, which Iran publicly acknowledged and which Western intelligence assessments had been tracking under various designations since its first observed deployments around 2019, was a delta-wing loitering munition of straightforward aerodynamic configuration. The airframe was constructed primarily from fiberglass and composite materials, reducing both manufacturing cost and radar cross-section simultaneously. The Delta platform, a triangular wing configuration with no separate tail surfaces, was mechanically simple to manufacture, structurally robust under the aerodynamic loads of level cruise flight, and produced a platform with a low wing loading that gave the vehicle sufficient lift at low speeds to cruise efficiently on minimal engine power. The propulsion was provided by a single pusher configuration piston engine mounted at the rear of the fuselage, driving a two-blade propeller in a pusher arrangement that placed the engine exhaust and thermal signature at the vehicle's tail rather than its nose, reducing its infrared detectability from the forward aspect that most infrared-guided interceptors approached from. Iranian state production used a domestic copy of the German Limbach L550E engine, a lightweight four-cylinder piston unit producing approximately 26 horsepower, sufficient to sustain cruise speeds of between approximately 160 and 200 kilometers per hour at altitudes of between 100 and 3,000 meters, depending on mission profile. The warhead carried in the nose section was a penetrating blast fragmentation charge of approximately 40 to 50 kilograms, sized to produce reliable structural damage to power infrastructure, fuel storage, radar installations, and unarmored military equipment without requiring precision delivery to the centimeter tolerances that hardened military targets would demand. The navigation system fitted to production Shahed 1. 3-6 vehicles combined GPS guidance with an inertial navigation unit that provided continued course maintenance in the event of GPS jamming or signal denial. The circular error probable of the system, the radius within which 50% of strikes would fall relative to the intended aim point, was assessed by Western intelligence agencies at between 5 and 15 meters under nominal conditions. This was not the accuracy of a precision-guided munition designed for point targets inside hardened structures. It was the accuracy of a weapon designed for area targets such as transformer yards, fuel tank farms, runway surfaces, and radar arrays. Installations where a 5 to 15 meter delivery error was operationally irrelevant because the target's vulnerable area exceeded the weapon's delivery error. The navigation system was not attempting to hit a window. It was attempting to hit a building, and with a circular error probable of 5 to 15 meters, it achieved that with consistency. The operational introduction of the Shahed 136 in the conflict in Yemen preceded its more widely documented use in Ukraine by approximately 2 years. Houthi forces in Yemen supplied with Shahed series munitions through Iranian logistics channels that the United States and Saudi Arabia were unable to interdict completely. Conducted attacks on Saudi Arabian oil infrastructure using combinations of Shahed 131 and Shahed 136 munitions from 2019 onward. The September 2019 attack on the Abqaiq oil processing facility and the Kurais oil field, which was attributed to a combination of cruise missiles and loitering munitions consistent with Shahed series characteristics, temporarily removed approximately 5% of global daily oil supply from production. The Saudi Arabian Patriot missile batteries defending the facilities did not intercept the attacking vehicles in sufficient numbers to prevent the strikes. The reasons for this failure were subsequently assessed by American and Saudi military analysts as involving a combination of the vehicle's low radar cross-section, their low-altitude cruise profiles that reduced radar detection range, and an attack geometry that approached from a direction and at a time that the defensive coverage did not optimally address. The Abqaiq attack produced a single operational conclusion that the subsequent 2 years of Houthi operations against Saudi infrastructure reinforced repeatedly. A Patriot PAC 3 interceptor missile, costing between $3 and $4 million per round, could destroy a Shahed series munition costing approximately $20,000. But the exchange ratio at which this trade became strategically sustainable for the defending side had not yet been established, because the defending side was spending more on each interception than the attacking side had spent on the vehicle being intercepted. The transfer of Shahed 136 munitions to Russian forces for use in Ukraine, which was publicly assessed by American, European, and Ukrainian intelligence agencies from the autumn of 2022 onward, and which Iran denied until April 2024, introduced the weapon into a conflict where the density of air defense systems, the sophistication of electronic warfare, and the volume of international analytical attention it received produced the most extensively documented operational record of the platform's capabilities and limitations to that point. Russian forces employed Shahed 136 munitions, which they redesignated Garin 2 in their own operational communications, in mass attacks against Ukrainian power generation and distribution infrastructure from September 2022 onward. The operational pattern was consistent and deliberate. Attacks were conducted predominantly at night, at low altitude, using multiple vehicles launched in sequence or simultaneously to approach target areas from varying directions, forcing air defense operators to engage successive contacts without the interval required to reset intercept solutions between engagements. Ukrainian air defense forces, employing a combination of Patriot PAC 3 systems supplied by the United States, NASAMS supplied by Norway and the United States, German Gepard self-propelled anti-aircraft guns, and improvised adaptations of Soviet-era systems, achieved interception rates that Ukrainian military sources assessed at between 60 and 80% of incoming Shahed series vehicles across the winter of 2022 to 2023. The percentage of vehicles not intercepted in those same attacks, between 20 and 40% of each wave, was sufficient at the volumes Russia was launching to produce cumulative structural damage to the Ukrainian power grid that required continuous repair operations throughout the winter and into 2023. The comparison with other loitering munition systems deployed by other states in the same period establishes the Shahed 136's position in the global inventory. With some precision, the American AeroVironment Switchblade 600, deployed by Ukrainian forces against Russian armored vehicles from 2022, carried a warhead of similar mass to the Shahed 136 but was designed for anti-armor rather than infrastructure attack, with a shaped charge warhead optimized for vehicle penetration rather than blast fragmentation effect against area targets. Its unit cost was substantially higher than the Shahed 136's assessed production cost. The Israeli Harop loitering munition, which had been in service since approximately 2009, and which had demonstrated operational effectiveness in the Nagorno-Karabakh conflict of 2002, carried a comparable warhead but incorporated a more sophisticated sensor suite, enabling it to autonomously detect and engage radar emissions. A capability the Shahed 136 did not possess in its standard configuration. The Turkish Bayraktar TB2, which had achieved international prominence through its operations in Libya, Syria, and Nagorno-Karabakh, was a reconnaissance and strike platform rather than a loitering munition, dependent on a ground control station and operating crew, and carried precision-guided munitions rather than functioning as a munition itself. None of these systems combined the Shahed 136's production cost, manufacturing simplicity, and launch volume in a single platform. The Shahed 136 was not the most capable loitering munition available in 22. It was the one that could be produced and launched in numbers sufficient to exhaust defensive inventories faster than those inventories could be replenished. The limitations of the Shahed 136 were consistent with its design priorities and were documented extensively through the Ukrainian operational experience. The vehicle's piston engine produced a distinctive acoustic signature at low altitude, a sound that Ukrainian civilian population networks learned to identify and report through social media and messaging applications within weeks of the weapon's introduction, providing ground-based early warning that supplemented radar coverage in the low-altitude regime where radar detection was limited. The low cruise speed, while efficient for range, made the vehicle susceptible to interception by systems with engagement envelopes that faster cruise missiles would have defeated, including the Gepard anti-aircraft gun system, whose 35mm cannon could engage targets at the Shahed that did not produce a direct hit. Near misses from proximity-fused ammunition that would have failed to destroy a conventional aircraft were sufficient to structurally compromise the Shahed 136's airframe and cause flight termination. These limitations were real and were exploited. They were also insufficient to prevent the weapon from achieving its primary strategic objective, which was not to destroy a specific target on a specific night, but to impose a sustained resource drain on defensive systems that no finite missile inventory could absorb indefinitely at the exchange. Ratios the weapon's production cost enforced. Israeli Air Defense Forces, which had been tracking Shahed series munitions in the context of Iranian supply to Hezbollah and Houthi forces for several years before the direct Iranian attack of April 2024, conducted after-action assessments of that attack, in which Iran launched approximately 170 Shahed series drones alongside ballistic missiles and cruise missiles in a single coordinated strike that were shared in partial form with American and Allied analysts. The assessments noted that the interception of the Shahed series component of the attack, while operationally successful in terms of vehicles destroyed, had consumed interceptor inventory at a rate that, if sustained across multiple attacks at a similar scale, would have required resupply timelines measured in months rather than days. The assessment was classified Its conclusion was not difficult to derive from the arithmetic of the exchange rates that had already been publicly documented. Between September 2022 and the end of 2023, Russia launched an assessed total of approximately 3,000 Shahed series munitions against Ukrainian territory. Western governments committed combined air defense support to Ukraine during the same period, totaling an assessed value of several $billion in interceptor missiles, radar systems, and associated equipment. The ratio between the cost of the weapons launched and the cost of the systems deployed to stop them was not recorded in any single document available to public assessment. The ratio is not difficult to calculate. It has not changed.